If you're taking a linear algebra course in college, pretty much a large portion of the course is just on solving and how to solve systems of linear equations. And so what that means, okay, well, you think linear, that's kind of line, things that are linear. And so here, right, we have y equals nx plus b, that's a line, another y equals nx plus b, a different line. Then we have a system of linear equations, meaning just a set of them. And typically you're trying to find a solution to all of them at the same time. So the same x, same y satisfies both equations. You can also have linear equations, and these are planes. So right, these are in three-dimensional space. They have x and y and z, each one of them. Here you have two variables, two unknowns. Here you need three variables, three unknowns to have a chance of having a unique solution, or yeah. So the way that you usually solve this first in high school is typically you'll set one equation to another, you'll figure out what the value of x is, and then you'll figure out what the value of y is. That's going to end up not being practical in this course, but let's go ahead and review that. So we're going to set equation 1 equal to equation 2. All right. And then we're going to try and solve for x, figure out what y is. Right, if the same x, y values work for both equations, then it's going to be the same y value on the left-hand side here, meaning that the right-hand side, the 3x minus 1 and the negative 2x plus 4, have to both be equal to each other. So we're going to have 3x minus 1 equals negative 2x plus 4, right? So to get started here, let's go ahead and let's get the x's to one side. So if I add 2x on this side, then I'll get rid of that negative 2x. I'll have to do the same on the other side here. So that'll get me to 5x minus 1 equals 0x plus 4. Right, next step, I'm going to add 1 to both sides to get the constants on one side of the equation. So that'll get me to 5x equals 4 plus 1, well that's 5. Last bit, I can divide both sides by 5, and that'll get me to x equals 1. Oh, well, that's good. So then from there, right, we have the x value. We should check that it works, and we did our algebra right. So let me just make some space there. Right, so we should have y is equal to, if I plug in 1 to both of these equations, we should get the same y value if I did all my algebra right. So this is going to be 3 times 1 minus 1. Right, plug in 1 for x into 3x minus 1. That ends up being 3 minus 1 is 2. And then same thing for this equation. Right, y equals, I have negative 2 times 1 plus 4. So negative 2 plus 4, that's also 2. So the solution here, the point that satisfies both these equations, is xy equals 1 comma 2. All right. So let's go ahead and try that on the next one. So here, right, this one we have kind of one step. We set the x stuff equal to each other, solve for x, and figure out y. This one, it's usually a little more involved. Sometimes you actually have to substitute kind of a, you set z equal to z, and then you substitute a function of x for y, put it into the third one. It's not very fun, but let's just get going here. So we have z equals 6x minus y, z equals 3 plus 2x minus y, and z equals 8 minus x minus 2y. All right, so let's just go and set equation 1 equal to equation 2 and try to go from there. So by doing that, we've essentially eliminated one of the variables already, right? We have z equals z, and those both equal these. So now we're down to 6 minus x minus y equals the second equation here, 3 plus 2x minus y. All right, we're going to get pretty lucky in this one. It's going to work out pretty nicely. So the first thing I want to do, I want to try and I can actually get rid of the y's. So if I add a y to both sides, right, so I have 6 minus x minus y, and then I add y, so that's just going to be 6 minus x. Then here I have 3 plus 2x. And I have negative y plus y again, so the y's actually are completely gone. So then from there, I can try and solve for x. So let me add x to both sides here to get the x's on one side. So that's going to be 6 equals 3 plus 3x. All right, then I want to get the constants on one side, so I'll subtract 3 from both sides. So I'll get 3, right, 6 plus negative 3 equals 3x Then I can divide both sides by 3. That'll get me 1 equals x. So we got pretty lucky there. Sometimes you'll actually get, x is a constant plus a constant times y, but we got lucky where the y's disappeared. But now we can go, so we've figured out one of these variables, and now we have to solve for one more equation here. So what I'm going to do next is I'm going to set equation 1 equal to equation 3, and go from there. So let me just get my chalk out. So set equation 1 equal to equation 3. All right, so z still equals z, so I have 6 minus x minus y equals, it's going to be 8 minus x minus 2y. All right, so the one thing though is I actually know that x equals 1, so I could just plug that in. So then I have 6 minus 1 minus y equals 8 minus 1 minus 2y. All right, so 6 minus 1, that's 5 minus y. 8 minus 1, that's 7 minus 2y. All right, well, to get kind of positive y's on one side, I'm going to add 2y to both sides. All right, so that's going to end up with 5, sorry about that, plus y, right, because I have negative y plus 2y equals 7, and then I have negative 2y plus 2y, the y's disappear. And sorry, I forgot, no, that's right. So then from there I'm going to subtract 5 from both sides to get the constants on one side. Minus 5. So then from there I'll get y. Right, the 5 and negative 5 cancel, and then 7 plus negative 5. Well, that's positive 2. So y is 2. And let me just eliminate that here. I'll need a little more room down here. So now if we've done things correctly, if we put x equals 1 and y equals 2 into all three of these equations, we should get the exact same z value every time. All right, so let's just double check that. So we have z equals, well, I have 6 minus x, which is supposed to be 1, minus y, which is supposed to be 2. And let's see, 6 minus 1 minus 2, 6 minus 3, that's a 3. Should also work in the next equation. So that's 3 plus 2 times 1 for x minus y minus 2. So that's 3 plus 2 minus 2, so that's also 3. And write z equals, what's the last one here? So 8 minus x, so 8 minus 1 minus 2 times 2. Well, I get 8 minus 1, that's 7, and then minus 4, that's also 3. So yeah, looks like I did my algebra correctly. And so the point that satisfies all three of these equations, the xyz point, is 1, 2, 3. All right, so this is the way that, the first thing you would try, and probably what you learned in high school. It's going to turn out that this method to kind of set equations equal and then try to get rid of one variable and go to the next equation is going to be quite laborious and won't be very practical. There's other ways to solve these. But next up, we're going to look at geometrically what it means when we solve these, and also change their form a little, because we can't represent certain things right now. Like we can't represent x equals 0 in this format, or x equals 3, because we kind of assume we always have 1 times y here. We also get certain planes here, because we always assume we kind of have 1 times z. So that's going to be the next chalkboard. Continuing from the last board, so we still have systems linear equations. We solved these in the last one. Not a great way to solve them, but let's go ahead and geometrically what it meant to actually do that. So in this one, right, we had y equals 3x minus 1 and y equals negative 2x plus 4. Our solution was at 1, 2, so that'd be 1, 2, so right about there. And then these are equations of lines, so we can actually draw those out. So in here I have 3x minus 1, so I actually need to extend that down, I think, a little. It's negative 1, negative 2. So we know when x is 0, the y value is negative 1. So one of the lines is going to have that point. And we also know when x is 1, y is 2. It goes through this point. And now one of the hardest things is to draw something going through more than one dot. All right. So that's one of the lines. It has a slope of 3 and the y-intercept of negative 1. All right, the other line, so we pick x is 0, then y is 4. Right, that's the y-intercept here. And we also know that when x is 1, y is positive 2. So it goes through that dot. So now, and let's see, when y is 0, that means x is 2. So I actually did an okay job drawing that line. All right. So those are the two lines. I'm going to make my dot bigger to make it look like it's going through the middle. But that's what we were solving. We were solving for the intersection of these two lines made by these two equations. And the other one's a little more difficult to visualize, difficult to draw. So the first thing here I want to point out, right, this has to be a right-handed coordinate system. So what I mean by that is, right, I could have put x here and y here instead. I could have flipped the labeling of these axes, but there's something called the right-hand rule. So you want, essentially, if you have, so in this one, the z-axis is going to come right out of the board. So the way the right-hand rule works is you put your hand extended on the x-axis, and it's my right hand, and if you curl your fingers towards the y-axis, then your thumb's going to point where the z-axis is. All right, so over here, it's a little harder because it's kind of in the board, but I start at y, and I curl towards, so start at x-axis, curl towards the y-axis, end up pointing up in the z-axis. All right, but let's try and visualize what it looks like when this gets solved. So the solution was that x, y, z equals 1, 2, 3. So it would be this dot. So, all right, and then 2, then 3. So the way that we can imagine this is I kind of start at x, and then it's going to have the same angle here, so something like that. Right, the angle right here has to match that angle. And so now we're at, that point is x is 1, y is 2, z is 0. And then we'll go up 3 units. So that's going to be right there at 3. And let me just explicitly label those. So 1, 2, 3. There's the dot. All right. So now we were intersecting lines in this one. This one's a lot harder to draw, so I won't. You're actually intersecting 3 planes. So I've got my little planes here. So a lot harder to figure out which way these are facing. I'm actually not going to try. But you essentially have 3 planes. And kind of if you draw any 2 random lines, they're going to intersect at some point. If you have 2 planes, that won't be enough to actually have a unique intersection. So in here, I've got my purple plane and I've got my yellow one. And if I have them touch each other, all right, and you have to pretend that this purple extends through the yellow one, but they're going to intersect in a line somehow. All right? And so that would give you an infinite number of solutions. And right, if you have, that would be kind of the situation where if I got rid of one equation, I'd have 3 variables, but only 2 equations. 3 unknowns, 2 equations, so there'd be an infinite number of solutions. So then why you need the third equation is when you actually intersect all 3. Let's see if I can do this with all my hands. All right. Let's see if I can get this to happen. Let's see. They're all going to intersect uniquely at some point. You do have to, remember these extend to infinity and they're going through the board. But that's the idea. So then these 2 intersect in a line, the purple and the orange one. And then the yellow one and the orange one intersect in a line right about there. Right, and the purple and the yellow one intersect in a line right there. But then all 3 of them only intersect at one point, and that's right here. And so in this one, it's really hard to draw 3 planes on a board. But essentially you have 3 planes intersecting, and 2 planes will intersect in a line, but a third plane will intersect that line at some point. It's going to be unique most of the time. So geometrically, that's kind of what is going on. Let me attempt to draw 3 intersecting planes. So I'm going to start with that one, so flattish. I'm going to have another one So then, it's going to extend down. Oh, oh. So there's another plane, and then if I have a third one, then I'll have something like that, that. I'm gonna, all right, let's see if I can do this. This might be working. All right, I did an okay job. So they're going to intersect uniquely at one point. Any two of them intersect in a line, but then if you put a third one in, essentially you have an infinite plane and a line going through space. Right, two planes intersect in a line, so if you have an infinite plane going through space and you have some line, eventually that line is going to intersect that plane at some point. So I said before that solving these systems of linear equations, even in this case, can be quite laborious, and you can end up with, very large systems of equations actually. And so we're going to change the format a little, and we're also going to come up with a better way to solve these that's a little tidier, a little faster. So the first thing is, right, we have this format here. We have it written now as y equals mx plus b. And there's a problem with this in that can't represent vertical lines. Right, probably remember this from high school. So you could set m equals 0, and then you can get, let's see, if you have y equals 0x plus 3, well, you can draw that, right? We have x, we have y, and so if that's 1, 2, 3, then the line y equals 0x plus 3 is this horizontal line. But there's no way to represent, if I have y and x, there's no way to represent this line. This is x equals -2, right? This was y equals positive 3. In this format, we just can't do it. The reason we can't do it is because we kind of just assume that this y always has a 1 in front of it, right? It's 1 times y equals some number times x plus some number times b. And that 1 there, that the fact that it has to be a 1, is actually making this unable to represent vertical lines. All right, so to get around that, so we can represent absolutely any line with absolutely any slope, any angle, we're going to change the way we write these equations. So instead of writing y and then equals something times x plus a constant, we're going to write these as something times x plus something times y equals a constant. So we're going to put the x and y on the same side. So to just do that really quick, I'm going to subtract 3x from both sides. So I'll end up with a negative 3x over here. I still have my plus y, and that all equals -1. All right, subtract 3x from both sides. Same thing here. I want to get the 2x over here, so I'm going to add 2x to both sides to cancel out the negative 2x. And I'll end up with positive 2x over here, and we'll have plus y equals positive 4. And now in this format, if I have a number times x plus a number times y equals a constant, not only can this represent all the lines that this one can do, right, which was pretty much anything that wasn't vertical, it can also represent vertical lines. So that's a plus, right? Vertical lines do exist, so I have to worry about them. It's also going to be convenient because it becomes a lot easier to actually solve the equations. There's a nice little trick that comes with it. And that trick is we're going to end up adding equations to each other and then storing those in the old equation. So let me just write that over here. So we have negative 3x plus y equals -1, and we have 2x plus y equals 4. All right, so what we're going to do is we're going to take equation 2 and we're going to subtract equation 1 from it, and we're going to store that, let me make my arrow a little longer, in equation 2, like it's this placeholder. All right, and then that's going to simplify. The reason I want to do that is if I take equation 2 minus equation 1, I can essentially subtract the left-hand side, the this left-hand side, now I can take this, there, let me just write it out. So, right, there's an equality here. So if I have equation 2, so the left-hand side of equation 2, which is 2x plus y, I'm going to subtract from it the left-hand side of equation 1, which is negative 3x plus y. All right, but I have to do that for both sides. So if I do, then I also have to take equation 2, the right-hand side was 4. I have to subtract from equation 2, equation 1. And so I have 4 minus negative 1, so we'll end up with 5. Let's go ahead and simplify this. So I have 2x minus negative 3x, well that's 5x. And then I have plus y minus positive y. I end up with 0y, which is what I wanted. I was trying to cancel out this y. And then on the right-hand side here I have 4 minus negative 1, so it's positive 5. All right. And then I'm going to rewrite both my equations. So I was going to take equation 2, I subtracted equation 1 from it, and I'm going to store my new equation in the equation 2 row here. All right. Excuse me. Okay. So I'm going to rewrite. So I have negative 3x plus y equals negative 1. And I have 5x plus 0y equals 5. So the next thing I want to do is I want to try and simplify this a little bit. And so what I'm going to do is I'm going to take equation, sorry about that, I think I inhaled some chalk. Dust. Alright, so, continuing on, we've got negative 3x plus y equals negative 1, 5x plus 0y equals 5. I do want to simplify this equation a little if I can. So we're also going to do, we're going to take 1/5 times equation 2, and we're going to store that in the equation 2 slot. All right, so we don't need to do a whole lot for that, right? If I multiply this entire equation by 1/5, we'll end up with, didn't touch equation 1, so I have negative 3x plus y equals negative 1, and here we'll end up with x plus 0y equals 1. All right, so from there we've actually solved for x, and if we want, we can just take x, plug it into this equation. We can also go back even further. We could actually cancel something in the equation above it, and we could just get y by itself. So let's go ahead and do that. So next we're going to take, I want to cancel out this negative 3x, right? Because I have an equation with just x equals a constant, and I want an equation of y equals a constant. So to do that, I'm going to take equation 1, and I'm going to add to it 3 times equation 2, right? Because negative 3x plus 3 times x will cancel out. And I'm going to store that in equation 1. All right. So if we do that, we'll have, I think I'll have enough room. So equation 1, so negative 3x plus y, and I'm going to add 3 times second right-hand side, second equation right-hand side, so x plus 0y, and that has to equal, all right, so I have to do the same thing to the right-hand sides. So I have equation 1, so negative 1, and then I have to add 3 times 1. That 1 comes from there. All right, so equation 1 plus 3 times equation 2, right-hand side, there we go. Now if we simplify that, we'll end up with, okay, well I have negative 3x, and I have a plus 3 times x, so those will cancel. So, and this is getting into equation 1, so I'm going to write it. So we'll end up with 0x, then I have positive y plus 3 times 0y, so I just end up with 1y. So I have 0x plus y. That's going to equal, I have negative 1 plus 3 times 1, so negative 1 plus 3, that's positive 2. So that's our new equation 1. Then I'm just going to rewrite equation 2 again. I have x plus 0y equals 1. And so from there you can actually just read off the solution, right? We don't have to worry about the 0x here, we don't have to worry about the 0y here, we just have y equals 2, x equals 1. So the solution is x comma y equals 1 comma 2. All right, so that actually may have seemed like more work since it was just two equations, two unknowns. But let's see what's going to happen with the other equation we had, the z equals, some stuff, and it was three equations, three unknowns. Now for the three-dimensional system. So again, we're going to change this. We're going to write this a little bit differently. And the reason for that is if we have, so in here, let's do z is equal to, let's say, mx plus, I'll do ny plus b. Sure, why not? So here, the m kind of controls the tilt in the x direction. The n in front of the y kind of controls the tilt in the y direction, and the b moves the plane up and down. But again, this one has a problem. It can't represent vertical planes. And what I mean by that is things like, x is equal to 3, y equals -4, or x minus 2y equals 7. And visually, what that means, so here I've got, there we go, I've got my little xy axes. So red, green, blue is x, y, z. This is a right-handed coordinate system, right? I start at x, I curl towards y, I go up in the z direction, there's my thumb. So right in this format, we can represent a whole lot of planes, a whole lot of them, in the axes, below, all sorts of planes. But there's actually a lot of planes we can't. So we can't represent a plane like this. This is going to be something like x equals positive 3. Or you can't represent a plane like this. This is y equals -4. And we can't represent pretty much anything that the plane is right up and down, because we need the coefficient in front of the z to be a 0. So right, that's a whole lot of planes we can't represent. And so by moving to a slightly different format, where we put all the variables on one side, we can represent all the planes we could before, plus all those vertical planes. So we're going to rewrite these as I'm going to move them all over. So I have, excuse me, I have x plus y plus z. That equals 6. I'm going to have, negative 2x plus y plus z equals 3. Then I'm going to have, x plus 2y plus z equals 8. All right. We're going to do something similar now to what we were doing before, and it's going to be a little more compact, and it's going to work out a little bit nicer most of the time. Especially, if we had a 4x4 system, it'd be even nicer. Still tedious, but works really well. So what I want to do is I'm going to have my top equation here. I want to try and cancel out all the x's in this equation and all the x's in this equation. So we're going to do equation 2. We're going to add 2 times equation 1, and we're going to store that in equation 2. And we're also going to do equation 3, and we're going to subtract equation 1, and we're going to store that in equation 3. All right, so the reason that I want to do that is if I take equation 2, so I have negative 2x, and I add 2 times equation 1, then I'll have 2 times x plus negative 2x. The x's will cancel. Then right here, I have equation 3, I just have 1x here, I have 1x here. So if I take x minus x, so equation 3 minus equation 1, I'll cancel out that x. The whole thing gets a little simpler. I'm going to store that in equation 3. So let's go ahead and write that over here. All right, so I haven't touched equation 1 either of these. I'm just going to copy it over. So I have x plus y plus z equals 6. All right, so now let's try and do this here. So I've got equation 2, so I have negative 2x plus 2 times equation 1, so negative 2x plus 2 times x. So the x's cancel, which is what I wanted. So that's 0x. And then I've got, all right, so equation 2, so I've got y, then I add to it 2 times y. So I'll end up with a total of 3y here, right? Y plus 2 times y. So plus 3y. Then the same thing for the z, actually. So I'll have equation 2, so I have z. I'm going to add 2 times equation 1. So 2 times z, I'm going to add that to z. I'll get 3z. And then for the right-hand side, I have equation 2, so I start with 3, and I add 2 times equation 1. So 3 plus 2 times 6, that ends up being 3 plus 12, that's 15. All right, so that's my new equation 2. Then for my new equation 3, I'm going to have equation 3 minus equation 1. So x minus x, so I got 0x, which is what I was hoping for. Then I've got 2y from equation 3 minus y from equation 1. So 2y minus y, that's just 1y. All right. Then I've got equation 3 minus equation 1. So z minus z. So I end up actually with 0z. All right, and that ends up equaling. So here we go, I have equation 3, so 8 minus equation 1. So 8 minus 6, that gives me 2. All right, so now I actually want to get this in a certain form. So the next thing I'm going to do is I'm going to exchange equation 2 and equation 3. All right, I just want to switch them. So if I do that, I'll end up with x plus y plus z equals 6, 0x. All right, I'm writing equation 2, I flipped them. So 0x plus y plus 0z equals 2. Then I'll have 0x for equation, from the second one in the third row. So 0x plus 3y plus 3z equals 15. All right, so did that. The reason I want to do that is I wanted to subtract this equation from the bottom one, the second from the bottom. All right. So now we're going to take equation 3, and I'm going to subtract 3 times equation 2. We're going to store that in equation 3. All right, so if we do that, we're not touching the top row. So we get x plus y plus z equals 6. We're not touching the second row, so we'll have 0x plus y plus 0z equals 2. Now we are touching the third row. So we have 0x minus 3 times 0x, so that we still get 0x. Now we're going to have 3y, right, from equation 3, minus 3 times y from equation 2, so that ends up with 0y, which is what I wanted. Then here, we end up with equation 3 minus 3 times 0z, so we don't subtract any z's that were 0z's, so we ended up with just 3z. But now we do have to worry about the right-hand side. So I have equation 3, so I have 15 minus 3 times 2. So that ends up being 9. All right. And now from there, we kind of have this nice format. We do have an x plus y plus z up here equals 6. Down here we have 0 plus y plus 0z. That could have been, non-zero, and we still would have had a pretty easy time. Now we have 0x plus 0y plus 3z equals 9. You can kind of read off the solution from here. So from the third equation, so equation 3, right on this side, that's going to imply that z equals, we divide both sides by 3, because z is equal to 3. then in equation 2, well, we know z equals 3, but it doesn't really matter. We can just read off here y equals 2. And then equation 1, since we know y and z already, it's actually pretty easy to figure out. We have x plus 2 plus 3, so we have x plus 5 equals 6. So subtract 5 from both sides, we get x equals 6 minus 5, x is 1. And so that wasn't too bad. We actually, I made this quite nice, so actually the substitution thing worked out well, but the substitution in general gets really horrible. So imagine if you had 4, variables and 4 equations. This thing is going to work out a lot better, but it's still got this kind of clunkiness to it. So we have to write x's and z's all the time. We have to write these, there's got to be a better way. And so the way to do that is actually with matrices. So you can actually write these systems of linear equations as matrices. So that's what we're going to do next. So we've solved this problem a few times now, right? This negative 3x plus y equals negative 1 and 2x plus y equals 4. And each time we've solved it, we've gotten a little more convenient, a little nicer way to solve it. And there's one more that we're going to do. So we're going to encode this thing as a matrix. So how to encode this as a matrix? Well, I'll just write it down. So we're going to have this square bracket here. I'm going to take the negative 3, put that in the top left. Then we have a plus 1 times y. I'm going to put a 1 there. And I've got a 2, so I'm going to put that in the bottom left. Then I have another plus 1 times y. I'm going to close the matrix off. I'm going to write another matrix. So x, y. So a lot of times, though, this is a matrix with just one column. Sometimes it's called a column vector. Sometimes it's called a vector. And then on the other side, I've got my 1 equals, and I have my negative 1 on top. I have my 4 on the bottom. All right. So what does this thing mean? So really, these are all 3 of these are matrices. They're just different sizes. This is a 2 by 2 matrix. So it's 2 rows and 2 columns. This is a 2 row, 1 column, so let's say 2 by 1 matrix, 2 rows, 1 column. And this is also a 2 by 1 matrix here. So the way that you use matrix equations is when you multiply it out, you end up with another column vector here. So let me just explain that. So I'm going to make, when I multiply this 2 by 2 matrix times this 2 by 1 column vector, I'm going to end up with a 2 by 1 matrix. So just bear with me here. So the way that you multiply matrices, let's say let's just do it here. All right. So I have my negative 3, I have my 1, 2, 1, and I have times x, y. All right, so that's going to equal a 2 by 1 matrix, and it's going to be a little wide. I'll try and scrunch it in there. And it needs to be a little wider. Okay. So this element here, it's going to be the first row, row of the 2 by 2 times the first column of the 2 by 1. Okay, that's a little weird. So the reason those are coming out, this is the first row, first column element of this matrix. All right, so if we do that, here's what we're going to do. First row of the matrix, this 2 by 2, times the first column of this other matrix. All right, so we're going to take an element-wise, so we're going to take negative 3 times x plus 1 times y. So again, negative 3 times x plus 1 times y. 1 y. So that is the first row, first column of the output matrix. All right. Then this one is going to be the second row of the 2 by 2 times the first column of the 2 by 1. All right, so when we do that, so second row times first column. It's only one column, but first column. So I have 2 times x plus 1 times y. All right, so 2x plus 1 y. All right, so if we simplify this bit here, when we multiply this out, this is the same as negative 3x plus y. This is 2x plus y. All right, we have this matrix times this vector xy equals this other vector, negative 1, 4. And then if you just look row by row, right, the first row of the matrix equation well, that's the, the first element here, the top element, the top row on this side has to equal the top row on this side. So it's going to be negative 3x plus y equals negative 1. All right? And the first row of the matrix equation, so that's that one. Got the second row of the matrix equation. All right, so we have to do this by rows, so we know 2x plus y equals 4. So it's just this very different way to write what we already had. Right, we had negative 3x plus y equals negative 1, negative 3x plus y equals negative 1. We had 2x plus y equals 4. We have 2x plus y equals 4. All right, it's kind of a weird way to get it. It'll make a little more sense with the 3 by 3. But essentially the first row, first column element in the resultant vector when you multiply a matrix times another matrix. First row, first column here ends up being the first row of this matrix times the first column of this matrix. Second row, first column here ends up being the second row here times the first column here. All right, so just to hammer this in, we're also going to do this for the 3 by 3 because that will show up a little better to solidify the intuition. We'd also like to write the 3 by 3 system as a matrix equation. All right, so to do that, right, we have these 3 equations, 3 rows. So we're going to need a 3 by 3 matrix. So that's going to be, and I take the coefficients from in front of the variables. So we've got 1x plus 1y plus 1z. So my first row is 1, 1, 1. My next row is negative 2x plus 1y plus 1z, so I get negative 2, 1, 1. And my third row is 1x plus 2y plus 1z, so I get 1, 2, 1. All right, so that's my 3 by 3 matrix. That multiplies x, y, z, and that all has to equal this right-hand side, so 6, negative 3, 8. And so right, we got a 3 by 3, we have a 3 rows by 1 column, and here we have another 3 rows by 1 column. If If we multiply this out using the way you multiply matrices, we'll end up with the equations we had back. So just to solidify that, let's go ahead and do that. All right, so here I have, I'm going to copy my matrix, so 1, 1, 1, negative 2, 1, 1, and 1, 2, 1. All right, times xy. Oh, sorry, x, y, z. All right, so if we do that, we're going to end up, right, we have 3 rows on this side, 1 column. We need to end up, to get them to be comparable when we multiply this matrix times this vector, it's also going to be a 3 by 1 vector, matrix on this side. So let's go ahead and do that. So right, the way you multiply a matrix times a vector, you just say, okay, I'm going to take the top row times the first column. That'll give me the element in the top row first column of the result of the product. All right, so that's going to be 1 times x plus 1 times y plus 1 times z. All right, element-wise, top row times first column, 1 times x plus 1 times y plus 1 times z. All right, so we'll end up with 1x plus 1y plus 1z. And let me just close it off. This is going to be a 3 by 1. Okay. So to get the second row of the result, so this is the second row, first column of this column matrix, right, single column. I'm going to take negative 2 times x plus 1 times y plus 1 times z. All right, element-wise, second row, first column, negative 2 times x plus 1 times y plus 1 times z. It's negative 2x plus 1y plus 1 z. All right, then if I want the third row in here, that's going to be the third row of the matrix times the first column here, the only column. So I get 1 times x plus 2 times y plus 1 times z. Right? 1 times x plus 2 times y plus 1 times z. So I get 1 x plus 2 y plus 1 times z. Okay? And then, right, we've expanded this out essentially, so we have, I'm going to drop, I'll keep the 1, sorry, 1x plus 1y plus 1z, negative 2x plus 1y plus 1z. And then I've got 1x plus 2y plus 1z. Right, that's all supposed to equal this right-hand side here, this 6, negative 3, positive 8. This is a 3 by 1 matrix, 3 rows, 1 column. This is a 3 by 1 matrix, 3 rows, 1 column. The reason they have to agree is kind of like comparing similar units. If you have to compare mass to mass, or length to length, or what's another one, volume to volume, you can't have a 3 by 3 matrix equal to just a 3 by 1 matrix. You have to have the same dimensions of a matrix equal to the same dimensions of a matrix. And now if you read these off row-wise, it's going to be the exact same equation we started with, right? So the top row, I'll say the first row, we end up with x plus y plus z. So the top element here has to equal the top element here, equals 6. That's this equation. The second row, we have negative 2x plus y plus z has to equal the second row here, negative 3. And then the third row, we have x plus 2y plus z equals positive 8, which is the third equation. So this right now is another way to write these matrix equations. So you have essentially the coefficient matrix, all the things in front of the x's and the y's and the z's, And then you have this xyz vector, your vector of unknowns. Then you have this right-hand side of your constants. So that would be your 6, -3, +8. Right, and it's this way to encode very compactly and nicely a bunch of matrix equations. Turns out, though, you can compact this even further. So we'll do that next. So we've done these equations quite a few times now. Every time we've done it, it's gotten a little bit easier, a little less writing to do, a little more compact. So we started with two equations here, so -3x + y = -1, 2x + y = 4. We were able to write that as a matrix equation where the coefficients on x and y are in this 2 by 2 matrix. Then we have xy equals, and this was the right-hand sides. All right. And now there's an even more compact way to write it. So we're going to write, it's called the augmented matrix. Okay, so we're going to have right here, this is going to be a row for equation 1. We're going to have a row for equation 2. And then this is going to be the coefficients in the variable x, the coefficients in the variable y. We're going to have a vertical bar, and this is going to be the right-hand side value. Okay, so we're going to copy. We have -3, 1, 2, 1, -3, 1, 2, 1. And then the right-hand side values are -1, +4. So -1, +4. So this is called the augmented matrix. So you have the equation 1, so it's -3 times x plus 1 times y equals -1, right, with this vertical bar. Equation 2 is 2 times x plus 1 times y equals +4. All right. Now, one of the nice things about this is you can really compactly write those row operations now. So we can write, if I want to cancel out this 2, then what I'm going to do is I'm going to say, okay, I'm going to take, let's see, 2/3 of row 1. So R subscript 1 refers to row 1. I'm going to add that to row 2, and that should cancel out this 2. We're going to store that in row 2. All right, so just if I write out the augmented matrix, the first thing I'm going to do is I haven't modified the first row, so I'm just going to copy it again. So I've got -3, 1, vertical line, -1. In the bottom row, all right, so I have 2/3 times -3. That ends up being a -2, right, because the 3 and 3 cancel, I end up with -2. So then I have -2 plus 2. -2 plus 2 ends up being 0. So we're going to store 0 in this spot here, which is what I wanted. I wanted to cancel this out. Then we're going to have 2/3 times R1, so 2/3 times 1. We're going to add that to 1, so 2/3 plus 1. That ends up being +5/3. Okay, and that's the coefficient now on the y in this new equation we're making. And then I've got 2/3 times -1 plus 4. Okay, so 4 is +12/3. So +12/3 plus -2/3 is +10/3. And so there's a new matrix equation, or augmented matrix equation, and I've got it simplified quite a lot. So I have 0x plus a number times y equals a number. So it's easy to figure out what y is from here. Y ends up being 2. Then I can go back to the previous equation, and I say, well, I don't know what x is, but I do know y. So you end up with -3 times x plus 1 times 2 equals -1. You can solve for x, which ends up being 1. All right, so a much more compact way to write this. So similarly, we can do the same thing for the 3 by 3. It's going to go a little bit faster. So we can write the augmented matrix. So I'm going to copy my 1, 1, 1, 2, -1, -1, 1, 2, 1, vertical bar, my 6, -3, 8. Okay, so these are the right-hand side values. And these are the coefficients on x in each equation, the coefficients on y, the coefficients on z. And this is the equation 1 row, this is the equation 2 row, and this is the equation 3 row. All right, so very compactly written. We're going to try and do the same thing. Okay, so I want to cancel out this 2 using the 1 in the top row. So what I can do is I can say, well, I'm going to take negative 2 times row 1 plus row 2, and we're going to store that in row 2. All right, so negative 2 times row 1 plus row 2, and we're going to store that in row 2. All right, so first thing to notice, I'm not modifying row 1 or row 3, so I'm just going to copy those again. And I'm going to make it a little taller so it's not so scrunched. All right. There we go. So 1, 1, 1, vertical bar 6. Vertical bar 6. I've got 1, 2, 1, 8. Okay. Now here we go. So negative 2 times 1 plus 2. Negative 2 plus 2, that's 0, which is what I wanted. I wanted to 0 out this element. So now we have to move on. So now I have negative 2 times 1, excuse me, plus negative 1. That ends up being negative 3. Then again, negative 2 times the row 1 element. Sorry, negative 2 times the row 1 element plus the row 2 element. So negative 2 times 1 plus negative 1 ends up being negative 3. All right, and then I have negative 2 times 6 plus negative 3. I think that ends up being negative 15. Okay, so I've done one row reduction there. Now I want to do another. I want to wipe out this one here using the one in the top row. So I'm going to have, looks like negative 1, times row 1 plus row 3. We're going to store that in row 3. All right, so first thing to notice, I'm not modifying row 1 or row 2, so I'm just going to copy those. So 1, 1, 1, vertical bar, 6, 0, negative 3, negative 3, negative 15. Okay, so now I'm taking negative 1 times row 1 plus row 3. So negative 1 plus positive 1 ends up being 0, which is what I wanted. So now I have to keep going. I have negative 1 times 1 plus 2. So that ends up being a 1. Yeah. Then I have negative 1 plus 1. That ends up being a 0. And then I have negative 1 times 6 plus 8. That ends up being positive 2. So we've row reduced, and a little bit. And so here, right, we can easily figure out what y is. Y is equal to 2. Then we can go back up to this next equation, and we say, okay, well, if y is 2, then I can figure out what z is pretty easily. So z ends up being 3, I think. And then if I know what y and z are, then I can go up to the top equation, which has all 3, and I have x plus 2 plus 3 equals 6. That's going to mean x equals 1. So it's really nice because you can kind of remove a variable every time you row reduce. And you reduce the rows, make them simpler, by trying to zero out stuff as you go along. And that's the idea. So this is augmented matrix, and this is a type of row reduction. There's a few different types. So we can go into that next, and there's going to be some more stuff on matrices. You know, this whole class is pretty much on matrices.